All right, welcome everybody. It's really great to see such a enthusiastic response for this idea. I just want to thank a few people who helped me put this together. Mark Sykes, the president of my company, PSI, was really enthusiastic about this seminar series. And Matt Perry is handling our technical things, and Pamela Gay helped put together a website for this. If you want to receive announcements for the future events, just send me your email in the chat, and I'll just share in the chat some information about this seminar series that you might like. So feel free to share it with others. So I'm sending you the homepage, the flyer, a Twitter announcement, and then there's a bunch of calendar events. So you should just be able to click on those calendar events to add those speakers to your calendar. And then just a preview for next week, we'll have Dhruv Balwada from Lamont Doherty Earth Observatory talking to us about direct evidence of an oceanic dual kinetic energy cascade from surface drifters. What else? We'll try to start on time and end on time. So try to get here, right at noon or a little before. And what else? Oh, and then after the seminar, we'll have a little coffee time. PSI has a space over at GatherTown, which is a really fun way to interact. So if anybody's interested in more informal chatting, it's completely optional. But after the seminar, we'll head over there and get the chance to meet each other. With that, I'll just introduce our first speaker. So Yohai Kaspi got his PhD from MIT in 2008, and then was a postdoc at Caltech from 2008 until 2011. He's now a professor in the Department of Earth and Planetary Sciences at the Weizmann Institute of Science in Israel. And I met Yohai kind of by chance about 2 decades ago while visiting his office mate, and was really impressed with the work he was doing at that time on Jupiter. And so I'm really excited to hear what he has to say for us today. His talk is entitled, "What Juno Has Taught Us About Jupiter's Atmospheric Dynamics." So yeah, feel free, go ahead, Yohai.
Thank you, Jonathan, and thank you for the invitation. And it's an honor to be the first one talking in this exciting seminar series. And yeah, so as you said, I'll be talking about what we learned from Juno about Jupiter's atmospheric dynamics. And this is, of course, an effort by many people on the Juno team and off the Juno team, trying to interpret the many measurements that we have from the multiple instruments on Juno. And I'll try and summarize what we have learned about the dynamics. I'll begin with a general introduction because I know that some of you are not thinking about Jupiter every day and night, and begin with just kind of introducing the planet. So it's, of course, a giant planet far away, 5.4 AU. It's giant. I put here, let me arrange the cursor so you can, okay, now I have a pointer. And it's a giant planet, so you can see here Earth. It's, of course, much bigger than Earth, just to give you the proportion. It's rapidly rotating, about 10 hours. And when we talk about rotation, of course, with a fluid object, where the reference is the magnetic field. So the magnetic field has a dipole, and this 9.2 hours is the rotation rate of that dipole. And the size and rotation period made this a really ideal geophysical fluid dynamical object. Obviously, the Rossby number is small. We don't have continents. We don't have the various complexities that we have on Earth. And this is really kind of an ideal lab for studying geophysical fluid dynamics, which is what makes it exciting, not only for planetary scientists, but also for Earth dynamicists, because it's such an ideal object. It's also very oblate, much more than Earth. and I'll get to that later when we talk about the magnetic field. And it's of course very massive, about 300 times Earth. What I'm showing here on the left are the zonal flows of Jupiter that you saw before in the movie. The blue are the zonal flows, the east-west flows as function of latitude. So going from about -50 to 150 meters per second in reference to that rotating frame that I mentioned before. And you see that you have about 6-7 jets in each one of the hemispheres. In red, I'm putting here the angular momentum conserving curve. So what this is the curve that you would get if you would take a fluid parcel from the equator and move it poleward. So as you're moving poleward, you're getting closer to the axis of rotation, and by that you're generating an eastward flow, and that eastward flow from this parcel at rest is called the angular momentum conserving curve, and you can see that it's much faster than the flows, except really at the equator. So that means that at the equator we need an extra source of angular momentum to make this flow go eastward, because otherwise any fluid parcel would not be as fast as we see at the equator. So I'll touch a little bit towards the end about the this region called the superrotation region. So we define superrotation as anything faster than this red line that you see over here. And of course, Jupiter was observed from a very long time ago. These are, I think, the first kind of pictures beyond, of course, the first one by Galileo published that I could find. So this is 350 years ago. You already see here these stripes that we see also today. Both images, by the way, both this one from a while ago and this kind of more modern one are from Earth observing platforms. So our ability to observe Jupiter has increased tremendously from back then. But pre-Juno, almost everything that we saw was looking from the outside, just looking from at the cloud level and trying to interpret what we see. There was only one probe that went. This was from the Galileo, which the Galileo probe went in at a specific point at a specific time. So we have only one single profile beyond that. So Juno was really the first mission to look deep into the planet. Now, what do we have beneath the cloud layer? Well, this is what we at least think that we have. There is some kind of a weather layer, which pre-Juno we did not know how deep it goes. Then there is a molecular regime. So this here is just hydrogen-helium mixture. And then the fluid becomes so dense, and this is just because of pressure, that it becomes metallic. So then beyond about 10% of the radius, there is this gigantic region here, which is metallic, and this is, of course, what's creating the dynamo and the giant magnetic field of Jupiter. And then maybe there is a core, and one of the missions of Jupiter is trying to figure out if there is a core or not, and what kind of core. So, of course, Juno has a lot of objectives. This is kind of a summary of the goals of the mission. But in this talk, I'm just going to focus about the atmospheric dynamics, or what I've written here as the deep dynamics. Because when we talk about an atmosphere, what do we actually mean when we have no surface? So I'm defining it, the atmosphere here, roughly as the region where we have dynamics, where things are moving, and we can talk about dynamics in the sense that we talk about an atmosphere on a terrestrial planet. Feel free, by the way, to ask questions, I guess, if Jonathan, if you want it to be that way, or
yes, of
whatever.
course. Feel free to ask questions anytime. Thanks for pointing that out, Yohai.
So I'm defining the atmosphere as, like I said, this region over here where we have dynamics. And Juno has 5 instruments which are relevant for this region. Of course, looking from the outside, we have a visible camera, the Juno camera, and an infrared mapper, the GIRAM instrument, coming from the Italian Space Agency. So those are both looking at more or less at the cloud level, what we can see, as I mentioned before, from the outside. Then there is MWR, a microwave instrument, and this instrument has 6 different channels, which you can see kind of illustrated here with different frequencies. These are different frequencies that it's probing. So each frequency is probing basically a different depth. So we can get a thermal map of Jupiter down to a few hundred bars. Okay, you can see this, by the way, this here is, we're going here 7 scales in pressure. So from about 0.1, or the cloud level is about 0.7, down to a megabar. So a megabar is roughly where this transition is happening here towards the metallic region. And MWR is probing from about the cloud level down to a few hundred bars. This is the microwave instrument. Then when the fluid becomes really dense and there's a lot of mass here, then the dynamics allow us, the dynamics at this kind of a depth allow us to get a gravity signal, because as they're moving, there are density gradients, and these density gradients are sensible by gravity measurements. And I'll talk later how this is done. And then when you go deep enough and the fluid becomes metallic, then the interaction of the flow and the magnetic field allow us to, through the magnetic measurements, to infer flows at depth. Okay, so this is kind of an important point about Juno. It goes from the very top to the bottom with very different instruments. And I put this a little bit schematically. Of course, there is some overlap between the different regions here. So Juno was launched back in 2011. It spent 5 years in orbit, and in 2016, it arrived at Jupiter, going into a very eccentric orbit. So it goes around the planet in this kind of a matter. During the prime mission, it did this every 53 days, when it's kind of zooming by the planet from pole to pole in about 2 hours. So most of the time it's spinning away from the planet, and then it goes very fast close to the planet, and that allows getting very close, about 4,000 kilometers above the cloud level of Jupiter. The prime mission ended actually just about 7 months ago. And now Juno is in a 43-day orbit after it passed by Ganymede and changed a little bit its trajectory. So it's now continuing. And because of the obliqueness of the planet, every perijove goes about, perijove is these passes by Jupiter, goes about 1 degree poleward in latitude. Okay, so if the first one was near the equator, it's drifting poleward and poleward. So we're like probing the planet at different longitudes, of course, and into latitude, that's increasingly moving towards the pole. And as the mission continues, this latitude will get very close to the pole, hopefully, if Juno survives for enough time. Now it's the extended mission. I'm not going to talk about this too much, just mention that this began last summer. And now the orbits are every 43 days, taking advantage of the fact that this orbit is tilted from an orientation which is near the equator to one near the pole, allows to fly by the different satellites. So Juno is going to flew by Ganymede, and then it's going to have flybys of Europa and Io later in the mission. So now the mission has become from just studying Jupiter to studying the whole Jupiter system in the extended mission. This is a movie of what you would see if you would be sitting on the Juno spacecraft. So Jupiter's obliquity is just 3 degrees. So basically, the terminator is sitting here very close to the pole, and you're looking down at the North Pole now in these 2 hours. We're now going to go on this 2-hour journey from pole to pole. This is the North Pole over here. You can see that the polar region is characterized by these vortices that were never seen before, because there were basically no good observations of the pole before Juno went into its polar orbit. Now the spacecraft is flying very fast and getting closer and closer to the equator. Now we're going into this region of jets, this kind of familiar red and white stripes of Jupiter. Now we're close to the equator. This is the Great Red Spot, already in the southern hemisphere. And now the spacecraft is going out, and you're seeing more and more of the southern hemisphere as it's flying away from Jupiter. So this kind of picture, which actually looks like an artistic, I don't know, something very artistic, but this is actual nature. This is the kind of picture that we're seeing from Jupiter every orbit. And of course, Juno flies at different longitudes. So the picture is a little bit different in features, but essentially the same kind of picture. And now you're seeing here the South Pole, and these are polar vortices which are surrounding the South Pole. This is a kind of a mosaic putting everything, all this you saw before together. This is another kind of amazing picture by Juno Cam, where you can see the different filaments, the turbulence going around here. You can even see kind of cloud tops, these white regions here are ammonia cloud tops. And you can see the shades of these, which might allow inferring height and stuff like that. There's a lot of detail in each one of these beautiful picture by Juno Cam. Then I mentioned the poles of Jupiter. So these are on the left, it's visible images from JunoCam, and the right, these are infrared images of the poles, the north on top and the southern and the south pole in the bottom. You can see the North Pole is surrounded by 8 circumpolar cyclones. Okay, so you have these cyclones going around here. These are all in cyclonic direction in the north, and then in the south, of course, cyclonic in the south is opposite. And you can see these very coherent structures sitting around latitude 84 in both hemispheres. And again, Juno was the first time that these things were identified, published by Adriani in 2018. And this was a mystery, like why do we have these stable cyclones and why do they sit in such a coherent way around the pole, and why do we have 5 in the south and 8 in the north?
And last question.
Sure.
Yeah, Yohai, is it always 8 in one hemisphere and 5 in the other one?
So
or it's just
we're seeing this picture every 53 days. And for as much as we could see, it seems like the 8 in the north is stable. Also the 5 in the south, but it happened twice that a 6th intruder came into the south and then disappear. And I'll explain why these are stable configurations.
Thank you.
This is another picture of the same thing. You're looking here at the North Pole, and you can see this kind of beautiful structure. I should also mention that beyond this, we also see these vortices extending to about 60. So at latitude 60, there's this transition from the region of jets to the region of vortices, but only near the pole, only from 84 north and south on, we see this very coherent structure that is stable. Okay, so what I want to focus in this talk are on 4 main questions that Juno allowed us to answer, or I should say to better understand. We never understand everything completely, of course. The first one is the stability and location of the circumpolar cyclones, which I just showed. And for that, this is, like I said, coming from the infrared measurements. I'll talk about the meridional circulation. So, on Earth, we have Hadley cells, Ferrel cells. We can now identify such cells also on Jupiter. So I'll show this, and this is coming from using the microwave measurement. I'll talk about how deep are the zonal flows coming from gravity. And then how deep is the red spot, which is a combination of gravity and microwave measurements. So I'm beginning with talking about the stability of the circumpolar cyclones. And like I said, in the north, we have 8, and in the south, we have 5. And for comparison, I'm putting here the pictures, which are not as great as on Jupiter, but from Saturn. And on Saturn, we have a polar cyclone in each one of the poles, but we do not have the circumpolar cyclone. So it's useful to compare the two in order to understand the dynamics. Before explaining that, I want to introduce the concept, which I'm sure many of you know, but for those who don't, of a beta drift. So if we have a background planetary vorticity, which are these blue lines that you see over here, so increasing with latitude, and you take a cyclone, you take a fluid parcel from the region of low planetary vorticity and you move it to the region of higher planetary vorticity, then you develop, and assuming that you're conserving barotropically, so this is the simplest kind of model, a barotropic model, you're conserving your overall vorticity, or your potential vorticity. Then what you get here in the region where you have, as you move the fluid parcel to a region of higher planetary vorticity, you're generating a negative vorticity region, so a flow in this direction. If you take a fluid parcel from above, you move it to a region of lesser planetary vorticity, then you have the opposite effect, conserving barotropically your potential vorticity, and you get this kind of a flow. So the combination of these two, this one going this way and this one going this way, I hope you can see my cursor, you're getting a flow towards the pole. Okay, so this is a beta drift. You can see here the combined velocity, and you're getting a poleward flow, a poleward beta drift of a cyclone. And this is a well-known mechanism, of course, for tropical cyclones on Earth. One of the reasons they're moving towards the pole is exactly this this beta drift, and there's a lot of literature about this in this context. So if we're thinking about the circumpolar cyclone, so labeled here CPC, versus the polar cyclone, PC, sitting at the pole, then this circumpolar cyclone is feeling the beta drift and moving poleward. But also, the presence of the PC also has a background vorticity. And this background vorticity can act exactly as the planetary vorticity and create a beta-like drift in the opposite direction. Now, as you move very close to the pole, of course, beta goes to 0. So the beta drift becomes very weak. And therefore, there is a latitude where you will be in equilibrium between this force and this force. And I'll show you that it happens that for Jupiter, this latitude is about latitude 84. Okay, so I'm using here the concept of a beta drift, but in a generalized way. For the polar movement, I'm talking about the regular beta drift. But for the equatorward movement, I'm talking about the beta drift induced by the polar cyclone, taking advantage of the fact that the background beta goes to 0, and therefore the weaker, usually, vorticity of the cyclone is giving you a background flow. So we can go and calculate actually these two forces given the data that we have about the cyclones. And what I'm showing you here is 4 cases: Jupiter North and Jupiter South, Saturn North and Saturn South, taking into account the size and vorticity of all the polar cyclones and the location. That gives you the strength of beta. So comparing here these two force, like this is not in units of force, but like proportional to a force, the beta drift and the gradient of the planetary and the gradient of the vorticity of the polar cyclone. So with this, when these two forces balance each other, that means 0, this line, you would expect to have an equilibrium point. So if we begin first with Saturn, you can see that we have no equilibrium. Always the force balance is in the bottom part of the plot, meaning it's going towards the pole. Meaning if you take into account the size and the polar cyclones of Saturn, they are such that they extend far enough that the beta effect is always stronger. So they always drift. So any cyclone coming here on Saturn towards the pole is always sucked into the polar cyclone, and you don't get an equilibrium point. But for Jupiter, you can see that we have 2 equilibrium points, one at latitude 84 and one at latitude 87 or 88. But notice that this one is not a stable equilibrium. Why? Because if you perturb it towards the pole, it's going to be moving more towards the pole, okay? Because on the bottom part of this plot, beta is bigger, and the top part of this plot, the gradient is bigger, and therefore this is not a stable equilibrium point. If you perturb it in this direction, it will end up at this point. But this point is a stable equilibrium, okay, for both the north and the south. So that tells you why these CPCs are stable right around latitude 84. Okay, so that's answering why we have these on Jupiter and not on Saturn, and also why latitude 84 is a special latitude. Remind you, this is somewhat not intuitive to us thinking about Earth dynamics, because we don't think about such high latitudes. You have the beta effect, but it's really going towards 0. You're almost here on an F plane, and therefore the vorticity of the cyclone itself is equivalent to the effect of beta, and therefore you get this kind of an equilibrium. Okay, so here I'm writing what I just said. Now let's talk about the stability of the cyclones going around around the latitude, why we have 5 and 8 in the other hemisphere. So for that, we're doing kind of the same exercise, looking at the force balance, but now instead of considering the beta, we're just considering the force that each cyclone is forcing on the cyclone right next to it. Okay, so intuitively, you can think that if you have just 2 cyclones, they won't really know about one another because they're far and away. And if you had, say, 100 cyclones, that will, of course, be unstable because they would be sucked into one another. So there should be some kind of magic number that is in stable equilibrium. So that's what we're trying to calculate here. So let's look at CPC, which we call CPC2, the force that it feels from number 1 and from number 3. These are these green and red lines over here. And you can see that with the exact same logic as before, if they're too close, then you have an unstable equilibrium. If they're far away, then you have a stable equilibrium. And it happens that this number, that's somewhere between this kind of 4 radius of a CPC to 6 radius of a CPC, becomes its 4 point something. So, and then you can calculate, given this distance that's stable between them, and given the circumference in the north and in the south, which is at about latitude 84, and the size of the polar cyclone, you can calculate how many cyclones you will find in north and how many you'll find in the south. And this equilibrium gives you about 8 in the north and some number between 5 and 6 in the south. Now I should say that we're taking here into account this, for this calculation, the size of the polar cyclone, which is not the same in the north or in the south. So in a sense, we removed here the question from asking why there are 5 and 8 to why is the polar cyclone bigger in the south than in the north. But anyway, given that size of polar cyclone, you can calculate that number and find these numbers 8 and about 5.5. What does 5.5 mean? It means that 5 is stable and 6 is unstable, but sometimes you can have an intruder. And indeed, like Pavel asked before, in 2 of the perijoves so far, and I think this also happened in the very recent perijove 39, there was an intruder and there was a 6th cyclone that came in, but this one is not stable. So we see it, but then when we look again 53 days later, it disappears. Okay, so that's addressing the question of the polar cyclones. Next, I want to talk about the jets. And what I'm showing here on the right, you see the clouds for reference, and you see the zonal flows that I showed before. This is the black line here. So we see these. This is just going up to latitude 60. So you see about 4 or 5 jets in each hemisphere, and I'm focusing here only on the mid latitudes, so from 20 to 60. And beneath that, I'm showing the eddy momentum flux convergence that was calculated 15 years ago by Ingersoll and Colette Salik, which was his student at the time. And they looked at data from Cassini images and were able to calculate the eddy momentum flux convergence. So this is what you're seeing here, or the Reynolds stress as function of latitude. And you can see a very good correlation between the momentum flux convergence and the flows. This means that the jets are eddy driven. Wherever you have a convergence of momentum, this thing here is positive, then you have an eastward flow, and a divergence, you have a westward flow, and this follows very well for everything in the mid latitudes. I talk mid latitudes, I call here from 20 to 60, basically. Okay, now in color here, I'm putting the places where the vorticity changes sign. Okay, so these are regions, not exactly the zones and the belts. It's kind of the opposite, but in a different way of defining it, going from the places where we have maximum vorticity, and I put this here in colors, and I'll refer to that in the next slide. Now, when we have an eddy-driven jet, okay, I'm going back again to give here an Earth example. So this is Earth's northern hemisphere zonal flows. So you can see these are the flows. This is the subtropical jet, and this is the eddy-driven jet. And in red, you can see, or in color, you can see the eddy momentum flux convergence in red and divergence in blue. And you can see that the eddy-driven jet is indeed eddy-driven, not surprisingly, by definition. But just to demonstrate the fact that we expect to have a momentum flux convergence where we have an eastward flow when it's eddy driven, but also that on Earth, this is accompanied by a ferrocell. So when we have momentum flux convergence, which is this term here on the right, so when this thing is positive, convergence, so this whole thing is positive, then that means in the northern hemisphere that we have an equatorward flow. So this is the flow up here. So we have this very good correlation between the convergence and the flow, and this is basically what's driving the ferrocell on Earth. So this is a mechanically driven cell, opposite to the Hadley cell, which is thermally driven in a whole different mechanism, which I'm not discussing. So then the question that you would ask, given that we have the momentum flux convergence over each jet, do we have a ferrocell over each one of the jets? And this is not a new idea. It was discussed in the past. Andy Ingersoll suggested it a long time ago. And then Leo and Schneider had a model, a GCM, which actually had ferrocell and replicated this. And this was discussed later also in a paper by Lee Fletcher just a couple of years ago. But we never had really good evidence for the ferrocells, except one important fact that was seen during the Cassini era, that we have lightning, meaning flow going up in places where you would expect it to go down just based on the clouds above. So that was some evidence for a ferrocell, but we didn't have, like I mentioned before, continuous evidence through all latitudes in order to find ferrocells. And we do have that now with the MWR, the microwave data. So let's see what we can do with the microwave data to figure out the ferrocells. So what I'm showing you here, this is a complex figure. I'll go through it slowly. On the left, we're looking at the background ammonia. Okay, so I should say that microwave measurements are mostly sensitive to ammonia. It's a mix of ammonia and temperature. It's a little bit of a sensitive issue. Here, I'm referring to them as if we're just now measuring ammonia, which is a tracer for the purpose of what I'm showing here in the atmosphere. And the background ammonia is looking like this. At the top, at the cloud level, we have, of course, ammonia clouds. We have depletion of ammonia, so the value is low. Then it goes up down to about a bar and a half. Then it goes down, and then it continues and goes up. So we have kind of this complex background ammonia. And theoretically, if we had ferrocells like the one I described on Earth and what we expect to find, then we would have a circulation which is looking like this. Now in colors here, you can see the background ammonia, just like in the measurement. And what you would expect, if it's indeed a passive tracer, that ammonia would be advected by these ferrocell, kind of tilting the lines of the measurements from the MWR. Okay, the brightness temperature, or what I'm referring to here as ammonia. And indeed, if you look at the measurements, what I'm showing here on the right is just again for the mid-latitude 20 to 60, and this is after removing kind of the background. So just looking at the ammonia anomalies, and you can see these wiggles, and these wiggles match very well these pink and blue regions, which I defined before based on the vorticity. Okay, so wherever we have an eastward flow and an eddy momentum flux convergence, we see also a very sharp change in the ammonia values. Okay, so that means we can interpret this as motion going up and down along these cells, like in the illustration here, advecting around the ammonia. You can see this in all channels, going from the very top all the way to the bottom, in both in the south and the north hemisphere. I'm kind of highlighting here maybe the best example, but you can see that this correlation is very good for all channels. And in this paper, there's a very detailed correlation analysis to really prove that this is a robust feature that we see in the atmosphere. So this points out that we have this up and down motion, which is exactly aligned with where we have the momentum flux convergence and the jets, exactly like we have ferrocells on Earth. To illustrate this better, I'm showing you here a model in the same paper by Dewar et al., where just focus here on panel B and C. So B is the data. Again, looking at the anomalies, taking the ammonia data and subtracting the mean, subtracting kind of this kind of zonal mean. And then this is a model which does not assume anything about ammonia varying with latitude, just assuming that the cells are sitting in the regions set by the momentum flux convergence and allow them to advect ammonia up and down, like you see here in panel A. And you can see that that reproduces very well the ammonia data. What you're looking here at the bottom is the same, but without removing the mean. So that kind of points to these cells that are sitting here. I should say that, and now this extends all the way to 1.5 bars to channel 5. Channel 6, this upper channel, has an opposite sign, meaning that the ferrule cells don't necessarily extend all the way to the cloud layer, but we're showing that the ferrule cells exist from about 1.5 bars to at least 100 bar, or as far as we have the MWR measurement, maybe much deeper. Okay. Now, again, I should caveat this by saying that I assumed here that the brightness temperature is all ammonia. And if there's a temperature effect, then it will be a little bit different. There's a recent paper by Lee Fletcher, where he investigates that kind of direction. And there he suggests that if you treat it more as temperature, so it can't be completely temperature, because if it was completely temperature, these variations will give you huge shear just by thermal winds. So it can be all temperature. But if it's somewhat temperature, a mix of ammonia and temperature, you can interpret these a little bit different, and then the ferrule cells extend maybe just to up to 6 bars, or somewhere between 3 and 6. And over here you would find a shear in the zonal flows. So and we don't know how much is ammonia and how much is temperature, but the fact that these variations match so well the places where you have the momentum flux convergence and divergence, and we understand the mechanism of a ferrule cell, gives us a strong hint that we're actually seeing ferrule cells extending very deep on Jupiter. Again, I want to go back and highlight the comparison to Earth, because I think it's really important, because we understand, of course, Earth dynamics much better. But now, when we have this evidence for Jupiter, we can do a comparison. So on Earth, of course, we have a Hadley cell, which is thermally driven, one ferrule cell, and then the polar cell. What I showed you is that the dynamics of ferrule cells that we know on Earth match very well what we see on Jupiter. And we see 8 cells in each hemisphere of Jupiter, both in the north and both in the south, based on the data I showed you before. So we have, wherever we have a westward jet, we have a circulation in this sense, and an eastward jet, we have a circulation on this sense, which we identify in the ammonia. This is just a movie, which I think illustrates this very nice, made by John Arballo at JPL. And if we kind of peer into Jupiter and leave aside the equatorial region for a minute and look at this east-west flows that we see here, you can really see in this illustration what I was describing before, these multiple ferrule cells, 8 ferrule cells rotating in different directions. So wherever we have a convergence of momentum, then we have a counterclockwise rotation. And where we have a divergence of momentum, meaning a westward flow, we have a clockwise circulation. Okay, so this is this idea of ferrule cells, and they're illustrated by the ammonia. Okay, so now I want to talk about how deep are the ferrule cells and the jets. When we talk about depth, then now we're going much deeper. So now we're going to be using gravity to understand this. I'm showing you here a picture of Jupiter and the zonal flows. Like I showed you before, these are the zonal flows that we see at the cloud level. So again, 6 jets in each hemisphere, with a very strong prograde jet at 23 north, a very strong negative jet, retrograde jet at 20 south. There's a big asymmetry here between the north and the south, and then the superrotation region that we see over here. Now, this asymmetry is important, and I'll get back to that in a few. I'll get that in a few minutes. To understand what's going on, let's look at the angular momentum balance. So again, it's basically the same equation as before, but now written in terms of angular momentum because it's more convenient. So this is the angular momentum of the background, and this is the angular momentum caused because of the flows itself. We can write the angular momentum balance. So we have here the mean circulation, some drag. This is again equivalent to Earth, but in Earth, instead of the surface drag, we're talking here about a drag because of the magnetic field at depth, and then the momentum flux convergence. And this is, I adapted this figure from Leo and Schneider, which I think illustrates this very nicely. So at the top, where we don't have the drag, then we have the balance between the mean and the momentum flux convergence. As I mentioned before, this creates the north and south flows, creating the multiple ferro cells. Then as you go lower, the momentum flux becomes weaker. You still don't have a drag, and then you just have this u dot grad m equals 0. Now, the surfaces of angular momentum are mostly parallel to the axis of rotation, meaning you're not going to get any flow across surfaces of angular momentum. So the flow is aligned with the axis of rotation. So when we think about these ferro cells, we're not talking about ferro cells which are radial, but we're talking about ferro cells which are aligned with the axis of rotation. And then when you get deep enough, then you have a balance between the first two terms, and then you can close the circulation, just like you close it on Earth, the ferro cells with the flow. So we don't have evidence that the ferro cells extend that deep. This is just a hypothesis. Now, I'm showing you this just to illustrate this kind of alignment with the axis of rotation, which I want you to keep in mind. I'm showing you here, this is out of kind of a deep GCM, just showing the multiple jets and how they decay with depth. They have a vertical shear aligned with the spin axis. The question is, how deep do these extend? So to understand that, we're going to be using the Juno gravity experiment. So here, it's basically not even an instrument. It's just the spacecraft itself is the instrument. The spacecraft is sending a radio beam to Earth, and through Doppler shifts of that beam, we're identifying small accelerations and decelerations in the movement of the spacecraft as it's orbiting in free fall Jupiter. And the instrumentation on Earth is sensitive enough to measure small variations which are caused by the flows. It's really kind of an amazing sensitivity of the instruments. And when we talk about a gravity field, what we use is the zonal harmonics. So we're looking here at gravity harmonics. For those not familiar with these J sub n's, it's just an integral over the density projected on spherical harmonics. Okay, and this density here has two components, one coming from the rigid body and one coming from the dynamics. Okay, so if we look at the gravity harmonics, they have this kind of a signal. The black line here is the sensitivity of Juno. Gray here is a model of a solid body model. Red are the measurements by Juno. So you can see that it pretty much follows the solid body for the even harmonics. This is a log scale, so full circles are positive and open ones are negative. But Juno also measured the odd gravity harmonics. So if you think about a fluid sphere rotating in space, it shouldn't have any asymmetry between north and south. The odds are asymmetry between north and south. The only asymmetry that exists is coming from the flows, because the flows have this asymmetry, which I pointed out before. So what I'm saying here is that these odd harmonics, 3, 5, 7, and 9, 3 of them are negative, 1 is positive, measured by Juno, are a pure signature of the flow itself. There's no other reason for an asymmetry in the flows. So given this, let's see if we can interpret these flows in terms, how we can connect the flows and these gravity harmonics. So the simplest thing to do is to take the winds that we see at the surface, because we don't know anything else about the flows, and then extend them into the interior along cylinders, as I explained before. And we can use thermal wind balance to relate the density anomalies and the shear. For those not familiar with thermal wind balance, this again, I'm going to an Earth example. It's a balance that holds very strongly for any rapidly rotating fluid, where we have a relation between the wind shear on the left, I'm showing you this here for Earth, This is from just reanalysis data. And the latitudinal temperature gradients. You can see this very strong match between these two figures. And we have no reasons to think that this will not hold on Jupiter. On the contrary, Jupiter is bigger, more rapidly rotating, so it has a smaller Rossby number, and we expect thermal wind to hold very well on Jupiter. So given that we believe thermal wind would exist on Jupiter, what we can do is take the cloud level flows, and again, this is the simplest model that you can think of, extend them on cylinders into the interior with some kind of e-folding depth. Okay, so we have here one free parameter, which is what we don't know how deep they go. Then use thermal winds to calculate the density anomalies, and then use this to calculate the gravity harmonics. And
just to let you know, Yohai, you've got 4 minutes left.
Okay, I'll try and speed up. So this is a prediction pre-Juno of what will be the wind-induced zonal gravity harmonics. The asymmetric part here, J3, 5, 7, and 9, and the symmetric part 6, 8, and 10. This is, as I said, pre-Juno. So intuitively, you should think that the deeper the flow goes, the more mass is involved, and therefore the gravity signal should be bigger. And this is generally what you see here, but it's not monotonic because of the fact that we're projecting something on cylinders and using spherical harmonics. So it's a little bit complicated, but generally, the deeper you go, the bigger the signal is. And then when the Juno gravity measurements came, you can see that, so these are these values, the 1 positive, 3 negative for the odds, and these are the even ones after subtracting the background. And what you can see is that indeed, all of them cross roughly at the same depth, somewhere between 1,000 and 3,000 kilometers, giving us an indication that the flows extend this kind of deep. I want to emphasize that each one of these is an independent measurement, and each one of them matches roughly the model saying the flows are a few thousand kilometers deep, both for the odds and for the even harmonics. Now, this was all done with a single parameter. So this is just with an e-folding depth, and we have here 7 free parameters, so we can go to more sophisticated structures. I won't have time here to describe these, but in general, the flows, and this is kind of the best fit that we find, the flows decay towards the interior. They begin rather barotropically, then somewhere between 2,000 and 3,000 kilometers, they decay and end up being very weak. There are more sophisticated ways of doing this, also including the magnetic field, but in general, that all the profiles, don't worry here about the details, just the fact, in general, you should remember that they're pretty barotropic and then decay when you go to depth. Then you can ask, okay, so they extend a few thousand kilometers deep, but is it the same signal that we see at the surface that extends deep into the interior? And what I'm showing you here is testing the statistical significance of this by taking random wind profiles that you see over here. The black is the regular profile of the cloud level. And I'll see if we can get the same kind of a result with a different wind profile. So this shows you the phase spaces of J3, J5, 3.7, 3.9. All these blue dots are these random profiles. The red is the Juno measurement with the uncertainty ellipse. And the black is the specific profile of the cloud level. And you can see that for most cases, the specific profile, this black profile, gives a much better match than the random wind profile. So indicating that what we see at the surface is extending deep. I won't have time to go into more detail, but we have refined this kind of analysis later on to show that actually what's important are the winds between 25 north and 25 south. So basically this asymmetry in the jets at 20 north, 20 south is practically what's causing the gravity signal that we're seeing. Although the higher latitude jets also have some contribution to this excellent match between the observation and the cloud level wind profile. Okay, so at this point, I'm running out of time, but I just want to mention that we have an analysis from Cassini for Saturn, which is important because it gives us very similar results. I'm not going to talk about details there, but just mention that for Saturn, we get a decay profile, which is similar to the one of Jupiter, but much deeper. And the reason it's deeper, so this is the profile that you saw before, and this, in the bottom here, I'm showing you the kind of the extension, the trajectory that goes deeper. The reason it's deeper because the conductivity on Saturn, okay, the region where it becomes conductive is much deeper because Saturn is not as dense. So it depends on the density where you get the ionized flow. So because this is, it shows here that the fact that from gravity we got a deeper flow on Saturn also matches the place where the conductivity rises. So this kind of is a strengthening this theory that the flows extend along cylinders until they decay by the magnetic field. And also the depth on Saturn matches the depth where if you would just extend a tangent cylinder from, and on Jupiter, same holds. If you would extend the tangent cylinder from the depth that we find from gravity, that is where the superrotation ends. So we have here like kind of two different regimes. So let me summarize. And I think this will be my practically last figure, just showing the different regimes that we learned on Jupiter, and same thing holds from Saturn. So for Jupiter, we find that the depth is about 3,000 kilometers based on gravity. Okay, so this I will call here, this is the dynamical region, or the atmosphere if you want. This is where we have the jets extending. This depth matches, and actually was predicted in a paper by Liu and Stevenson, even before, just because of the fact that this is the depth where the magnetic conductivity, where the electrical conductivity rises. So if again, you take this tangent cylinder out here, this is the region where you have a superrotation. So this is the region which was this kind of red, the eastward flow in the previous figure. So this is one dynamical region. I didn't have time in this talk to explain why we have equatorial superrotation. It has to do with momentum fluxes coming from the inside and being converged here, giving you superrotation. We found that in this region up here, where the jets are, the multiple jets, that's where we have ferrocell. So each jet is associated with a ferrocell. So this mid-latitudes are a region very similar in some sense to what we have on Earth. But on Earth, we have only one ferrocell. Jupiter is bigger and more rapidly rotating, can hold more ferrocells. So we have these east-west jets associated with opposite ferrocells in the mid-latitudes. And then beyond latitude 60 or 65, we have a whole different region dominated by cyclones. And then at the pole, we have these circumpolar cyclones, which I explained. So with that, I think I should end. I had one more slide to explain the Great Red Spot, but I can do it as an answer if someone, the depth of the Great Red Spot, if someone wants to see that. Thanks.
Wonderful. Thanks so much, Yohai, for that really beautiful and interesting talk. We have time for a question.
Please show the red spot.
Okay.
Thank you for your talk. Yes.
Sure. So this is just one slide. So Juno had 3 flybys over the Great Red Spot, one with microwave, which you can see here on the right, and you can see the visible on top, and then the 6 different channels, and you can see the signature of the Great Red Spot going down at least to almost all the way down. So at least a few hundred kilometers deep, we can identify the Great Red Spot in the microwave. And then later on, this was PJ7. Then later on, there were 2 dedicated flybys for gravity over the Great Red Spot. And this was a really ambitious experiment because we're trying here to identify the Great Red Spot, of course, is a mass anomaly. So we're trying to identify in the same way as before through gravity, perturbation because of this mass anomaly. PJ18 was lower, but a little bit further away. PJ21 was higher, but right on the Great Red Spot. So they were pretty equivalent. And both of them, you can see here, gave a little bit of a delta V. So the spacecraft was flying above and got a slightly bump just because of the existence of this mass anomaly. And then we could translate back this little bump in velocity to how much mass is in the Great Red Spot, integrate that down, and find that the depth is about 300 kilometers, plus minus 100 kilometers, or let's say with 3 sigma, definitely less than 500 kilometers deep. So
oh, you can go ahead and ask the question. Whoever had their hand up, I just lost it. Imeric?
Yes, can you hear me well enough?
Yes.
I can, yeah.
Yes, okay. Hello, Yohai. Bonjour from Paris. And thank you very much for this amazing talk. I was really amazed by your explanation of the vortices in Jupiter. But my question is not on that. I was intrigued by the fact that you find in your gravity signatures that the flow is much shallower close to the pole. And I was wondering what would be the dynamical implication of that, and if you have some thoughts about that.
Okay, well, first, of course, by definition, at the pole, it has to be 0, right? Because we have no zonal flow right at the pole. This analysis, this is the best match that we got for the gravity data. I should say that this is not as robust as the depth itself. So with the depth, you can maybe change this curve with different assumptions a little bit, or with adding the magnetic field, it becomes a little bit more barotropic on top. But there's no way to match the gravity data without going a few thousand kilometers deep. Here, it's a little bit more sensitive, because after all, you have only 4. You have here, this is based just using J3, 5, 7, and 9. So if you have 4 constraints, I could put 100 free parameters and give you some kind of wiggles, but it won't mean much. So with those constraints, you get a better match if you have a deeper flow at the equator, and you can see also the uncertainty here, which is growing. But also remember that the jets only extend, or the main jets extend only to latitude 60 or so. So we don't, and we see more the vortices at the higher latitudes. So you won't expect to have a much deeper flow near the pole.
Yeah, we have a question from Larry. Go ahead.
Yes, this is Larry Army from Scripps. I have a question regarding the difference between the northern and southern hemisphere. In the northern hemisphere, you have a very fast jet ranging in latitude from about 19 to 24 degrees.
Yeah.
Here. Whereas in the southern hemisphere, you have the equivalent of an oceanic meddy, which is the Great Red Spot, and no such anomalous jet. Can you comment, please, on why this large difference between the northern hemisphere and the southern hemisphere?
Well, I don't think we know why we have this kind of a difference. I think dynamically we understand what sets the width of the jets, and that has to do with Rhine scale arguments. So the size of the jets, and which also varies a little bit with latitude, is well understood, but there's no dynamical reason, I think, that at a specific latitude, 20 or 30, you should have a jet go necessarily north or south. So I think this is somewhat randomly set, and if we come back 1,000 years from now, this might be different. That we have a northern flow here and a southern flow here. I don't think this has to do with the Great Red Spot. The Great Red Spot is sitting here because it's sitting exactly, its anticyclonic direction fits exactly the shear that we see over here. But the fact that this is negative is not because of the Great Red Spot. It's just sitting within these 2 jets. But I don't know, maybe someone else knows about a dynamical reason why the north would be positive and the south would be negative.
Could I comment on the width argument you just made, which I don't buy, because the fast jet at about 23 north is much, much narrower than the equatorial band. And yet the speed is a little bit faster, actually, than the equatorial superrotation speed. Do you have an explanation for that? Because the width is much smaller.
Yes. So at the equator, I think the dynamics are going to be completely different. Once you're outside of the tangent cylinder, as I mentioned at the beginning, you need a momentum flux convergence to drive the jet, but it's not for the same reasons as up here from the ferrocells. Down out here, what you have is I can show that. Well, I guess maybe in this. What you have here is you have, because of the convection, you have convective flow going up and down along the direction of the axis of rotation, and here I have actually an extra slide showing that a little bit. Well, this is a mechanism for the superrotation, but what you would have outside of the tangent cylinder, and in this particular case I'm showing you here, it's just a much wider region. You have a flow which is in direction perpendicular to the axis of rotation. So you're not talking here about momentum flux convergence in the direction that you used to think about for jets going north-south, but because you're in a deep atmosphere, you have here these convective cylinders. And this is a hypothesis, right? But these convective kind of cylinders, which are tilted in such a way that they create an angular momentum flow towards the outside. And the width, I think, of the superrotating jet has to do with this kind of asymmetry of, so it has to do with, this depth. The place where this tangent cylinder is set by where the conductivity begins. So if the conductivity begins 3,000 kilometers deep, then you would get the superrotating jet from this latitude, which happens to be around 17, north and south. In Saturn, evidence for that is the fact that on Saturn, where the conductivity is deeper, the superrotation is wider. And therefore, on Saturn, you can imagine this gray area being smaller, so you have more superrotation, and therefore you have the momentum flux going outward in that region. Okay, so I don't think comparing the width of this jet to the width of this jet is evidence against Rhine scaling setting up the width of the jet.
Great.
Thank you very much. That's very helpful that you're pointing to an entirely different mechanism than, namely the multiple jets and ferrocells for the cause of that higher speed jet.
This is Andy Ingersoll. Can I expand on Larry's question a little bit? I put something into the chat. You really have to look at the curvature of the westward jets, because that's second derivative of the velocity. In the westward jets, you're comparing that curvature with beta. It's a slightly different thing than the Rhine scale, but it has dimensionally the same thing. And that curvature is slightly greater than beta at many of the westward jets, which means that the barotropic stability criterion is violated. It doesn't mean the flow is unstable, but just the simple barotropic stability criterion is violated at the westward jets, but it's not as dramatic a curvature as at the eastward jets. Hope that helps.
Yeah. Yes, of course, beta is positive. So on one side you have that asymmetry in between the curvature, and that's I believe why in the westward jet you get a kind of a more round jet and a more pointy jet in the eastward jet. But you're right, the barotropic stability, I mean, if you compare UY and beta, that doesn't hold for most of them.
Could I make thanks, Andy. Does that mean that, in fact, we should consider these potential vorticity jets, of course, and that the use of the planetary beta is not sufficient for understanding the westward jets?
There's the vertical structure, and there's the barotropic stability criterion is not sufficient. I think we all know that. There's baroclinic effects.
Let me just jump in here. I'm really happy to see such an enthusiastic discussion. I propose we make a transition now. I do like to kind of keep things according to the schedule. So I think it's a great time to say thanks again to Yohai. For anybody that came in late, I'll share in the chat some information about the upcoming events in this series. If you want to be reminded by email of them, please just put your email in the chat. When we have these meetings virtually, one thing that everyone says is that it's difficult to get the kind of interaction time that you normally are used to getting. Luckily, my company has a really wonderful space called GatherTown, where you can do more like hangout time. So if anybody is interested in heading over there, we can continue conversations there and have a little coffee break for the next 10 or 15 minutes. So I'm sending you the link now to GatherTown. Just a note about that, it doesn't work well with Safari, so please open it with a different browser. And if Matt, you could just leave this on for a little bit so people can get the information, that would be great. But at that point, I think we should move on towards the informal part of the conversation. And thanks again to everyone who came. This was really a great hit. So I really appreciate the enthusiasm.